Welcome to module 3 of chapter 7. In this module we are going to discuss two important concepts. One is planar graphs, other is coloring of a graph. A graph is said to be planar graph if you draw the edges of the graph in a plane such that no two edges will cross over. Now it is known that a complete graph K4 is isomorphic to wheel graph. So K4 is a planar graph. So all graphs with 4 or less vertices are automatically planar graphs. There is only one graph with 5 vertices is not planar, that is K5. In module 3 we study planar graphs and coloring of a graph. The learning objectives of this module are planar graphs and Euler's theorem, dual of a planar graph, coloring of a graph and 5-color theorem. Definition of a planar graph: a simple graph is said to be planar if it can be drawn in the plane such a way that edges do not cross. Every tree is a planar graph. Since K4 is isomorphic to W3, all graphs with 4 or less vertices are planar. Cycle graphs, wheel graphs are also planar. So now we will show that K5 and K33 are not planar graphs. We will show their K5, K33 are not planar after a while, but at this moment we will see we will assume they are not planar and we will see different properties of these K5 and K33 not planar. These are the simplest non-planar graphs in different ways. First of all, K5 is a non-planar graph with the smallest number of vertices and K33 is a non-planar graph with the smallest number of edges. So now we will see, verify that these two graphs K5 and K33 have the following properties. Both are regular, that is easy to see. K5 is a 4 regular graph, K33 is a 3 regular graph. Both are non-planar, that we will establish after a while. The graph obtained by removing exactly one edge or one vertex from K5 or K33 is a planar graph. K5 is non-planar graph with smallest number of vertices. K33 is a non-planar graph with smallest number of edges. Thus both are simplest non-planar graphs. A planar graph divides the plane into various connected regions, one of which is called exterior region. Every region including the exterior is bounded by edges. For example, here this K4 or isomorphic to W3 is a planar graph which dividing the plane into 4 regions, R1, R2 and R3, R4. R4 is the exterior region. Each region is bounded by some edges. So, for example, R1 is bounded by 3 edges, R2 is bounded by also 3 edges, R3 as well as R4 is also bounded by 3 edges in this case. So, we can call them as degree of the region. So, here the degree of each region is also 3. The degree of the region is defined as number of edges which forms its boundary. So, sum of the degrees of all regions is equal to again twice the number of edges. Since each edge is on boundary of exactly 2 regions, so the proof easy. A tree and a null graph determines just one region in the plane, the exterior region, and every edge of the tree is a part of boundary of this region. Now we will see Euler's theorem. Since a planar graph, not only vertices and edges, regions also involved. So Euler theorem gives the relation that for the necessary condition for the graph to be a planar graph, let X be a connected simple planar graph with mod V vertices, mod E edges and R regions, then mod V minus mod E plus R is equal to 2. We will see the proof. We will use induction on the number of edges. If mod E is equal to 0, then X is K1 and the graph with one vertex and one region. Why it is going to be K1? It is because we are assuming graph is connected. So, no edges means it has to be K1 only. So, clearly it has one vertex, one region. So, mod V minus mod E plus R is equal to 1 minus 0 plus 1, that is equal to 2. So, the result is true. If mod E is equal to 1, then the number of vertices in X is 2, the number of regions is 1. In that case also the result is true, that is mod V minus mod E plus R is equal to 2 minus 1 plus 1, that is equal to 2. Assume that the result is true for all connected simple planar graphs with fewer than mod E edges, and let X be a simple connected planar graph with mod E edges. Case 1, suppose X is a tree, then mod E is equal to mod V minus 1 and R is equal to 1, as planar representation of tree has only one region. Thus, we have mod V minus mod E plus R is equal to mod V minus mod E is mod V minus 1. So, plus 1, what is equal to 2. So, the result is true. Case 2, suppose X is not a tree, then X has at least one cycle. So, let C be a cycle in X, let E be an edge of C. Let X minus E, the graph X minus E, by deleting edge, that edge from X has only one edge less than the number of edges of the graph X. Also, the number of vertices in X minus E is and X are same, but the removal of the edge E merges two of the regions of X into one in X minus E. Therefore, X minus E has one region less than that of X. Thus, by induction hypothesis, X minus E we have mod V minus mod E minus 1 plus R minus 1, that is equal to 2. Hence, we have mod V minus mod E plus R is equal to 2. Hence, the result follows. Now, as an important application of this Euler's theorem, let X equal to V comma E be a connected simple planar graph with mod V greater than or equal to 3 vertices and mod E edges, then the number of edges is less than or equal to 3 times mod V minus 6. Since in a planar graph every region is bounded by at least 3 edges, we have 3 into R is less than or equal to 2 into modulus of E. Thus, using Euler's theorem, we see that 3 times 2 minus mod V plus mod E is less than or equal to 2 into mod E. Just we replaced the R value in the previous equation, 3R is less than or equal to 2 times mod E. So, which implies mod E is less than or equal to 3 into mod V minus 6. So, this result is giving an upper bound on the number of edges for a planar graph. So, number of edges should be less than or equal to 3 into mod V minus 6. Proceeding on the lines of the proof of previous corollary, we obtain the following result. Let X be a simple connected planar graph and let the length of smallest cycle or girth is R. In the previous case, we assumed that the length of smallest cycle is 3. So, we can extend that result to any other graph now with the smallest cycle length is R. In this case, mod E is less than or equal to R by R minus 2 into mod V minus 2. It is easy to see that if R value is 3, then we have previous result. So, if the girth is R and which is greater than 3, then number of edges is still less than the earlier corollary. So, another corollary is that every simple planar graph contains at least one vertex of degree less than or equal to 5. This is another important characterization of the planar graphs. In the planar graph, there is at least one vertex of degree less than or equal to 5. Proof for this one, suppose that degree of every vertex is greater than or equal to 6, that is small delta of x is greater than or equal to 6, then using the previous corollary, that is 6 times mod V is less than or equal to 2 times mod V, which is less than or equal to 6 into mod V minus 12, that is a contradiction. So, there is at least one vertex whose degree is less than or equal to 5. The degree of vertex of a complete graph Kn is n minus 1. Hence, Kn for n greater than or equal to 7 is not a planar graph. Now we will show that K5 is not a planar graph. Earlier we assumed it is not planar, but now we will show that is direct consequences of corollary 1. If K5 is planar, then it has to satisfy modulus of E is less than or equal to 3 times modulus of E minus 6. But in K5 note that number of edges are 10, number of vertices are 5. So, 3 into 5 minus 6, that is 15 minus 6, 9. 10 is less than or equal to 9, that is a contradiction. So, K5 is not a planar graph. Thus, we note that the graph K6 is also not planar and so on. Now, we will use corollary 2 to prove that K33 is not planar and Peterson graphs are also not planar. So, main result is that K33 is not planar, and by using that we can also show that K33 is Peterson graph is also not planar. Since K33 is a bipartite graph, it has no triangles, so girth is greater than or equal to 4. Hence, but actually in K33 girth is exactly equal to 4. Hence, if K33 is planar, then we must have that number of edges has to have at most 8, that is 4 by 4 minus 2 into 6 minus 2, that is equal to 8. But K33 has 9 edges, thus K33 is not planar. We know that girth of Peterson graph is 5, thus planar drawing of Peterson graph can have at most 5 by 5 minus 2 into 10 minus 2, 43 by 3 edges. But Peterson graph has 15 edges, so clearly 40 by 3 is less than 15 by 15, so it is a contradiction. So, Peterson graph is going to be non-planar graph. So, now we define a concept called homeomorphic graphs. Let X be a graph and V be a vertex of degree 2. Suppose n of V, that is neighborhood of V, equal to u comma w and u is not equal to w, then the edges uv and vw are said to be in series. Deleting the vertex V and replacing the edges uv vw by uw is called a series reduction. The opposite of series reduction is an elementary subdivision. It consists of replacing an edge uw with two edges uv and vw, where V is a new vertex that is added to get two new edges. Two graphs are said to be homeomorphic if each graph can be obtained from the same graph by a sequence of series reductions or equivalently obtained from the same graph by sequence of elementary subdivisions. For example, any two cycles are homeomorphic. Since K22 is isomorphic to K4, it is homeomorphic to K3 or C3. Korotowski's theorem: a simple graph is planar if and only if it has no subgraph homeomorphic to either K5 or K33. An example show that a graph on the which is drawn below is non-planar. So, graphs are given like this. We have to show that this graph is not planar. So, now we are going to prove this by using Korotowski's theorem. So, if you look at the another graph on the right, it is easy to see that this graph is obtained from the first graph by series reduction, and this graph contains K5 as a subgraph. So, this graph has a K5 as a subgraph by on series reduction. So, original graph is not planar graph. So, again we will repeat, it is easy to see that given graph is homeomorphic to graph that appears on the right that contains K5 as a subgraph. So, by previous theorem this graph is not planar. Show that Peterson graph contains a subgraph which is a subdivision of K33. So, this leave it as an exercise. So, one can check easily that Peterson graph contains a subdivision of K33. Now we define another important concept, that is dual of a planar graph. Given a planar graph X, we can define another multigraph X star as follows. Corresponding to each region R of X, we obtain a vertex R star of X star. Corresponding to each edge E of X, there is an edge E star of X star, that is two vertices R star and S star are joined by an edge E star if and only if their corresponding regions R and S are separated by an edge E in X. A loop is added at a vertex R star of X star for each cut edge of X that belongs to the boundary of the region R. So, few properties of dual graph. Let E star and R star, modulus of R star and modulus of E star, and mod E, mod R, mod V denote the number of edges, regions and vertices of X star and X respectively. Then we have number of edges in X star, that is modulus of E star, which is equal to the number of edges in X. Number of vertices in X star is equal to number of regions of X. So, degree of a region, degree of a vertex in X star is equal to degree of the region in X. Moreover, if X is connected, the number of regions in X star is equal to the number of vertices in X. An edge forming a self loop in X yields a pendant edge in X star. Pendant edge in X yields a self loop in X star. Edges that are parallel in X produces series edges in X star. Parallel means multiple edges with the same vertices, and two or more edges are there, then we will say they are in parallel. Edges that are parallel in X produce series edges in X star. X star is a planar graph. Let X be a connected planar graph, then X is isomorphic to its double dual, that is X star whole star. The proof is easy. Let X be a planar connected graph and X star is dual of X. Now, any region R of dual of X star contains exactly one vertex of X, namely the corresponding vertex V in X. This is because number of regions of X star is same as number of vertices of X. Thus, in the construction of X star star double dual of X, we will take a vertex V to be the vertex in X star star corresponding to region R of X star. These choices gives us a required isomorphism from X and X star star. A connected graph X is called a self dual if it is isomorphic to its dual. One of the nice example is K4. K4 is self dual. The next result characterizes bipartite graphs of duality in terms of duality. A simple connected planar graph X is bipartite if and only if its dual X star is Eulerian graph. So, X is a simple connected bipartite graph, then X does not contain odd cycles. Since X is a planar graph, all the regions of X are of even length. So, the degree of every region in X is even. Let X star be the dual graph of X. Since vertex degrees of X star are same as corresponding degrees of regions of X, the degree of every vertex in X star is even, hence X star is Eulerian. Conversely, assume X star is Eulerian, then degree of every vertex in X star is even. Since degree of every vertex in X star corresponds to degree of region in X, the degree of every region in X is even. So, thus shows that X contains only even cycles, hence X is bipartite. Every planar graph divides the plane into various regions. One of the region is exterior region. Consequently, every planar graph has at least 3 parameters, that is number of vertices, number of edges and number of regions. Euler proved that every planar graph satisfies mod V minus mod E plus R is equal to 2. Now, we are going to discuss another concept called coloring of a graph. Coloring of a graph means we have to color the vertices in such a way that adjacent vertices will not have the same color. Now we will introduce another concept called coloring of a graph. A k coloring or k vertex coloring of a graph x is a mapping alpha from vertex set of x to k, where k means the set 1, 2, 3 and so on up to k. The coloring is said to be proper if the adjacent vertices obtained distinct colors. That is, for all uv belongs to edge set of x, alpha of u is not equal to alpha of v. A color I belongs to k, the set k, that is 1, 2, 3 and so on k, is said to be available for a vertex v if no neighbor of v is colored by I. A graph x is said to be k colorable if there is a proper k coloring of x. The vertex chromatic number denoted by chi of x is defined as chi of x equal to minimum k, there exists a proper k coloring of x. If chi of x equal to k, then k is said to be k chromatic graph. Each proper vertex coloring alpha v of x to k provides a partition of vertices v1, v2, vk of vertex set v of x, where vi is equal to v belongs to v such that the color of the vertex v is I. So, in that way coloring of a graph, proper coloring of a graph is going to give a partition of the vertex set. Note that chromatic number of x equal to 1 if and only if x is a null graph. A graph with at least one edge has a chromatic number greater than or equal to 2. Bounds on chromatic number. It is easy to check that the following conditions. Chromatic number of x is always less than or equal to number of vertices. We do not require more than number of vertices colors. Chromatic number of complete graph is exactly equal to n. This is the graph requires more colors. It is because in complete graph every vertex is adjacent to every other vertex. If a subgraph of x is k chromatic, then chromatic number of x is greater than or equal to k. If degree of v equal to d, then at most d colors are required to color the vertices adjacent to v. Chromatic number of x is maximum of c, where c is a connected component of x. So, sometimes graph may be disconnected. In that case, the chromatic number is equal to the maximum of the chromatic number of the connected component of x. Every k chromatic graph has at least k vertices v such that degree of v is greater than or equal to k minus 1. So, we are going to prove certain results on the chromatic number. Chromatic number of x is less than or equal to delta of x plus 1. So, it is nice to see as an exercise what are the graphs exactly this bound will achieve. Chromatic number of x equal to delta of x plus 1. One example clearly we can see is Kn. In the complete graph delta of x is n minus 1 and chromatic number of complete graph is equal to n. So, in that case we have equality, and also one can check that this is for the cycles of odd vertices, that means C3, C5, there also this equality holds, and now try to find out are there any other or only these two is a nice problem to explore. So, for any graph we have chromatic number of x is less than or equal to delta of x plus 1. Let x be any graph with n vertices. To prove the result, we will use induction on n. For n equal to 1, x equal to k1, chromatic number of x equal to 1 and delta of x equal to 0. Therefore, result is true for n equal to 1. Assume the result is true for all graphs with n minus 1 vertices, and let x be a graph on n vertices. Therefore, by induction hypothesis, for a fixed vertex v of x, we have chromatic number of x minus v, that is we deleting the vertex v, is less than or equal to delta of x minus v plus 1. Thus, this shows that x minus v can be colored by using delta of x minus v plus 1 colors. Since delta of x is maximum degree of vertex in x, vertex V has at most delta x neighbors in x. Thus, these neighbors use up at most delta of x colors in the coloring of x minus V. If delta of x equal to delta of x minus V, then there is at least one color not used by the neighbors, V's neighbors, and that can be used to color the vertex V, giving delta of x plus 1 coloring for x. In the case that delta of x is not equal to delta of x minus V, that is then delta of x minus V is less than delta of x. Therefore, using a new color for V, we have delta of x minus V plus 2 coloring of x, and clearly delta of x minus V plus 2 is less than or equal to delta of x plus 1. Hence, in both the cases it follows that chromatic number of x is less than or equal to delta of x plus 1. The following statements are equivalent for a simple connected graph x. X is 2 colorable, x is a bipartite graph, and every cycle of x is even length. We already know that a graph is bipartite if and only if every cycle is even length. Now, it is easy to see that bipartite graph means we divide the vertex set into two sets such that individual sets are not adjacent. So, we can give same color to V1 and another set, another color. So, two colors are sufficient to color the bipartite graph. So, that is also easy to see. Again, if a graph is two colorable, we are using only two colors to graph the coloring, then it is easy to see that the vertices with one color and versus other color will give the bipartition of the graph x. Now, we will show that the chromatic number of Peterson graph is 3. So, here it is easy to see we already colored with 3 different colors. So, Welch-Powell algorithm, this algorithm is going to give us how to proper coloring of a graph. So, the input is a graph is given with 10 vertices. Now, we need to, this algorithm tells us how to color the graph. First, order the vertices according to decreasing degrees. So, assume D1 is the highest degree, D2 is the next highest degree, and so on, dk. Such an ordering may not be unique. Use first color to color the first vertex, and to color in sequential order each vertex which is not adjacent to previously colored vertex. So, first we exhaust one color to many vertices. Repeat the process using second color and remaining uncolored vertices. Continue the process with the third color and so on. So, Welch-Powell algorithm is a greedy algorithm which is used to color the vertices, but it may not be the optimal, but it is one of the algorithm. Now, we are going to show that every planar graph is 5 colorable. The following result establishes every planar graph is 5 colorable. This statement means that if x is a planar graph, then chromatic number of x is less than or equal to 5. In fact, the famous 4 color theorem states that every planar graph is 4 colorable. So, theorem, every planar graph is 5 colorable. Proof, we will prove the result by induction on the number of vertices. Since every graph with 5 or less vertices need at most 5 colors, hence the result is true for the base case. Let x be a planar graph with k greater than or equal to 5 vertices, and assume that all planar graphs with less than k vertices are 5 colorable. Since x is a planar graph, by using previous corollary, it contains a vertex of degree less than or equal to 5. We proved that every planar graph contains a vertex whose degree is less than or equal to 5. Let this vertex be V. Then by induction hypothesis, x minus V by deleting the vertex V from x is 5 colorable. Now, we need to color V. If degree of V is less than or equal to 4, we are done. As neighbors of V colored with at most 4 colors, so fifth color can be used to color the vertex V. If degree of V equal to 5 and its neighbors need only 4 colors, then also we are done. The only case left is degree of V equal to 5 and the neighbors of V need 5 colors. We will show that this case is not possible by showing this condition will lead to a non-planar graph. Suppose neighborhood of V is equal to A, B, C, D, E with the neighbors of V. Also suppose that we used colors 1, 2, 3, 4 and 5 to color the vertices A, B, C, D and E respectively. Now in the graph x minus V, there is a path from A to C whose vertices are alternately colored with 3 and 1. We will show in a figure. Now without loss of generality, we assume that the cycle obtained by the union of alternating path from A to C and the edges AV and VC contains the vertex B. Then we cannot have a similar path in the graph x minus V between the vertices B and D, as x is a planar graph. Hence, B and D can be colored with the same color too. So, just look at the diagram, we will understand that one. So, here V is the vertex, the coloring done like this means A is colored with color 1, B is colored with color 2 and C3, D4 and E5, and there is a path from A to C with colors only with 3 and 1. In that case, we cannot draw an edge from B to D. If you draw that edge, then it is going to, then it will, there is a crossover. So, it is not going to be a planar graph. So, B and D can be colored with the same color, that is what we are doing. So, consequently, V can be colored with another color. So, thus we are left with color 4 which can be used to color the vertex V, hence the required result follows. It is known that every planar graph is 4 colorable, but its proof is difficult. It is of the belief that this is the first theorem proved by using computers. Instead, we proved every planar graph is 5 colorable. With this, we end this module.